So last couple things from 3-1. You're going to see a couple problems like this on your Math Excel when you get to it. All right, so this one says, you have 100 yards of fencing to enclose a rectangular section of a field. What is the maximum area you can enclose, and what are the dimensions of the rectangle if you want to enclose this area? So we had some area problems. I can't remember what section it was in. At some point in maybe like chapter 8, we were doing the systems. Something like this came up, so it's kind of similar. It is helpful, I think, to draw the rectangle. And we don't know what the dimensions are, so we can just put x's and y's. They could be equal. We don't know if, x is the same as y or they're different. We'll just generalize here. And there's two things that we're concerned about in this problem. 100 yards of fencing, which is what in the context of this problem? 100 yards is what? Perimeter. Okay, so if you write a perimeter equation for this, you would add up all the sides. So that would be 2x plus 2y, and that equals 100. Okay. The other thing that we're concerned about in this problem is area, and all we can do for area is x times y. That's it. Now the problem is asking us to maximize the area. So we somehow need to get that perimeter information into the area equation. So we're going to use substitution to do that. To use substitution, we got to get a variable alone. It doesn't matter what variable you get alone. Let's say I want to get the x alone in this equation. How would I get the x alone? Subtract 2y, so 2x equals 100 minus 2y, and then what? Divide everything by 2. So x equals 50 minus y. That you can plug into the area equation. That's going to give me area equals 50 minus y times y. And if you distribute the y through, you get 50y minus y squared. And there's the quadratic. That's why it shows up in this section. Okay. Anytime you want to either maximize or minimize a quadratic, what point are we calculating? The maximum on a parabola is called what? The vertex. Okay, so that's all this is asking. If it asks for a max or a min, depends on the way your parabola opens, it's asking you to calculate the vertex. We have the equation. We learned yesterday, or we reminded ourselves yesterday, how to find the vertex. So the vertex formula, if you remember, was negative b over 2a. What's the opposite of b in this problem? Be careful because terms are a little out of order. A is the number in front of the squared term, B is the number in front of the variable that's not squared, and C is the guy that's all by himself, which I don't have a C in this problem. I only have an A and a B. Yeah, so A is -1, B is 50, so -50, and then A again is -1. Okay, again, my terms are a little out of order, but I can find those. -50 over -2 gives me 25. That's the x coordinate of my vertex. It's also the x value up here in my picture that's going to maximize the area. So now you have two options to find the y that goes with it. Well, to find the y value, I guess, at the top. Option number 1 is you can plug 25 into the area equation. Let's go ahead and do that. If I plug 25 into my area equation, I'm going to get area equals 50 times 25 minus 25 squared. Okay, 50 times 25 gives me 1250. 25 squared gives me 625. Subtract them, you get 625. That is the maximum area. 25 is the dimension, and if you look up here, they're all going to be 25. If everything's 25, 25 by 25 will give me an area of 625. And if I'm asked for dimensions, it would be a 25 by 25 rectangle. So depending on how MathXL asks it, either one of these are what you're being asked for. 25 by 25 dimensions or 625 square units is the maximum area that can occur. You guys can see that from the quadratic, okay? Once you have one, either the x or the y, you can always plug it back into the perimeter equation too to get the other one. If I know both of them are 25, I could multiply those together to get the 625. I don't have to use my area equation, so you kind of have some options here because it's a word problem and you've got that picture to help you. You don't have to use the function. I just kind of like to because that's what we're learning about, right? That's the big idea here, okay? Any questions on that problem? Okay, the other one we didn't get to yesterday was this one. It says, from the top of a building, a projectile is shot 400 feet high, from 400 feet high, with a velocity of 64 feet per second. The altitude height after t seconds is given by the following function. So they filled out that information for us. You guys may have seen this in Algebra 2. The last number is the initial height, which is where it's shot from here, 400. The middle number is the initial velocity, which they told us that, so you can see where those were filled in the equation. The negative 16 is a constant that has to do with gravity, is where that number comes from, so that's always in these formulas. You won't have to fill them in, though. These will be given to you. All right. It says, what is the maximum height of the projectile? Okay, so again, I'm asked for a maximum, so I'm calculating what? Vertex. And this one's a little bit easier because I already have the equation. I don't have to create the equation myself. And even better than that, it's all in order for me. What's the opposite of B? Negative 64. And then A is negative 16. So I'm going to have negative 64 over negative 32. I get 2. Is the x, or the t coordinate of my vertex. Okay. T stands for seconds. That's not what this question is asking for. The 2 tells me after 2 seconds is when it's going to reach its maximum height. The y coordinate represents the height, and that's really what this question is asking for. So you do have to go back and plug that 2 in. Negative 16 times 2 squared plus 64 times 2 plus 400. That's going to give me negative 64 plus 128 plus 400. I get 464. And that is our answer. We would label it feet. Okay, so after 2 seconds, it reaches 464 feet, and that is the maximum height of the projectile. All right. Part B, when does it hit the ground? When something hits the ground, what's the height equal to? 0. So this is kind of a fancy way of saying we're going to find an intercept when something is equal to 0. So you are setting the equation equal to 0 and solving for t. That's kind of gross. You have 2 choices, I would say. Factor, which I think would be kind of gross because of the large numbers we have here, or quadratic formula. If I'm looking at this, I'm going to use quadratic formula. I'm solving for t, a time. I'm not going to have radical answers anyway. If I told you the answer was like square root 3 seconds, that would be ridiculous, right? A decimal would be appropriate here. So quadratic formula kind of lends itself to this kind of equation, especially because it's a real life situation. So let's use our quadratic formula to solve. Instead of x, it's t. T equals opposite of b, negative 64, plus and minus square root. B squared is 64 squared, minus 4 times a is negative 16, times c is 400, all over 2a, 2 times negative 16. All right, I'm just going to type that whole square root in my calculator. Square root of 64 squared minus 4 times negative 16 times 400. And like I said, I don't care if this is a decimal or not. I get 172.33 about over negative 32. And then I simplify once with the plus and once with the minus. Negative 64 minus 172.33 divided by negative 32. gives me 5.57. Nope, that's the one with the minus. Right in the wrong spot. 5.57. If I simplify with the plus, negatives, no, hold on, don't write that down. I didn't type it in my calculator right. Sorry, guys. I put -6 and not -64. -64 minus 172.33 divided by -32. It's bigger. 7.39. Okay. If I type it in with the plus, -64 plus 172.33 divided by -32 gives me -3.39. And these are both seconds. Time. Do both of those answers make sense? What doesn't make sense? Yeah, it's not going to hit after negative seconds. Does that number work in the equation? Yeah, but does it make sense in real life? No. It's outside of the domain. It's outside of the domain. Sure. Because the domain of t is 0 to wherever it hits the ground at, which is 7.39 seconds. So that is the only answer. Okay, so although we get two answers, we want to just relate that back to, does that make sense in our situation? Only a positive time period would be an answer. And let me put up the deadline for when 3-1 is due. 3-1 is the only assignment that's going to be due this week as far as Math Excel, guys. That's due on Friday. And like I said, Friday is going to be Math Excel work day for you. Okay. All right, so that wraps up 3-1 quadratics. That's the stuff we didn't get to yesterday, just a couple little word problems. Any questions on that or anything that popped up in Math Excel so far with quadratics that we need to worry about? Okay, so then what we're going to do for the rest of the period is get a head start on 3-2. Hopefully we can get half this done today, half tomorrow. You won't have to watch any videos on your own. Get your Math Excel work day on Friday. Life will be good. That's our goal. All right. So polynomial functions are what we're starting with here. Okay. You don't really need to write any of this down just yet. We're going to get to this in a minute. Okay. So what is a polynomial function? The formal definition is written up there. F of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1. All the way down to a sub 0. What that means is a polynomial is a number times a variable to a power, plus or minus. A number times a variable to a power, plus or minus, so on and so forth. So an example of a polynomial, and this is what I would write down, example, because we'll use this example to kind of name some terms here, would be this. -3x to the 7th plus 4x to the 5th minus 3x to the 4th plus 2x squared minus 5x minus 8. Okay, number times a variable to a power, plus or minus number times variable to the power. This is what we call standard form of a polynomial when my exponents are in decreasing order, descending order. Highest exponent first, lowest exponent last. Okay, a sub n x to the n is called the leading term. In my polynomial, the leading term is -3x to the 7th. It's the guy that has the highest power in the term, okay? So not necessarily the first. Sometimes they're not in order. It's the guy that has the highest exponent. That's my leading term. It's the whole thing. The leading coefficient is the number in front of that term, -3. The constant term, sometimes you have these, sometimes you don't. It's the guy that doesn't have a variable. So in my polynomial, the constant term is -8. Okay. We can also name the degree of this polynomial. The degree of my polynomial is 7. It is your highest power. So that first term, that leading term, is going to give you most of your information. The leading term contains the leading coefficient. It also contains the degree. The only other piece of information we need is the constant. That's going to be the guy that does have a variable. We have a couple special cases. If you have a horizontal line, so like f of x equals 8, okay? Just making something up there. Y equals a number, horizontal line, the degree is 0. Okay, so because I can put an x to the 0 at the end of it if I want to. Anything to the 0 power is equal to 1, so that doesn't change it. The only guy that has no degree is f of x equals 0. That is the only polynomial that has no degree. Polynomials have special names. We've used them. Constant function is our horizontal line. Linear function was a degree of 1, power of 1. Quadratic, that we did yesterday, is a degree of 2. And then they start to get bigger. If we have a degree 3, we call it a cubic. That was one of our basic functions. Degree 4 is quartic. Degree 5 is quintic. And then after that, we don't really use the special names. We just say degree 6, degree 7, whatever. Okay. All right. Notice all of the exponents here. All of the exponents are non-negative integers. If you have something that is not an integer or it is negative, it is not a polynomial. Okay? All of the exponents must be non-negative integers to make it a polynomial. So the next type of question we're going to look at in a minute are, I'm just going to give you some examples. You're going to tell me yes or no if it's a polynomial. The exponents a lot of times are going to give it away if it is or is not one. Everybody good on this? Okay. Polynomials also have a couple other interesting facts. The domain will always be all real numbers. That's nice for us. We don't have to worry about any domain restrictions. No fractions, no variables in the denominator anyway, no square roots. Domain all real numbers always. Also, the graph will be a continuous, smooth curve. Continuous means I can trace it without picking up my pencil. Smooth means it does not have a sharp corner. Okay, an example of a graph that you know that has a sharp corner is the absolute value graph. The absolute value graph is continuous. The domain is all real numbers, but it has a sharp corner. It is not a polynomial. Okay? So domain is all real numbers, continuous, smooth curve, no sharp corners, if we're looking at its picture. Yes? Yes, so all of these are functions. A polynomial is a function. So if it didn't pass the vertical line test, it would not be a function. It would not be a polynomial. Good question. Okay, so let's look at some examples. And you don't really need to write these down. Maybe the last two you can write down. Do you think the first one, x cubed minus 1 over x minus 1, is a polynomial? Yes or no? No, it's not. Can you give me a reason why? It's a restriction, yeah. X cannot equal what number? Here. Which number? 1. X can't be 1 in that denominator. Make the denominator equal 0. And shouldn't the domain be all real numbers? So your explanation could be the domain is not all real numbers. X can't be 1. Okay, what about the next one? Polynomial or no? No? Why not? Again, restrictions. X can only be numbers greater than or equal to 0. The domain is not all real numbers, not a polynomial. The domain is going to give this away. What about the next one? Not a polynomial. Why not? Yeah, so our exponents had to be non-negative integers. That's a negative integer. The other thing you can think about is, if you remember talking about exponents back in like algebra 1, to make an exponent positive, we move it to the denominator. So 3x to the negative second power is the same thing as 3 over x squared. If I see it like this, you could also say there's a domain restriction. X can't be 0. Okay, but that negative exponent's the problem. What about the fourth one? Polynomial or no? Looks like it fits our form. Exponents look good. No domain restrictions. This is a yes. Usually we want to put it in standard form. So I'm going to put my negative 7x to the fourth first, minus 5x plus 3. Okay. What is the leading term? Negative 7x to the fourth. What is the leading coefficient? Negative 7. What is the constant? 3. What is the degree? 4. And so if I were going to give this a name, I would say this is a quartic function. That's a degree 4 polynomial. Okay, make sense? All right, what about number 5 there? F of x equals 8. Is that a polynomial? Y equals 8. Horizontal line. Is that a polynomial? That's one of the special cases I gave you. Yes, it is. What's the degree? 0. The leading term is 8. The leading coefficient is 8. The constant is 8. It's all 8. Degree 0. What about the one at the bottom? Polynomial or no? Did we have any restrictions with coefficients? Did we talk about that at all? No. The pi looks weird, but it's okay. We're allowed to have whatever number we want in front of the variables. So yes, this is a polynomial. What's the leading term? Pi x to the third, the whole thing. The leading coefficient, pi, what's the constant? 4, what's the degree? 3, you're getting it, good. You're gonna have a lot of questions in Math Excel just like this. Yes or no, why or why not, what's this part of the polynomial, all that stuff. Okay, any questions on that? Identifying a polynomial and its characteristics. All right, good. Moving on. Okay, actually I'm gonna skip over this slide. We are gonna do something in a minute called the leading term test, and I'll come back to that. The leading term test helps us determine what's happening at the ends of a polynomial. Now tomorrow we'll figure out what's gonna happen at the middle of a polynomial, but polynomials are continuous, they're gonna go on forever, and something's gonna happen at the ends. 4 things can happen at the end of a polynomial. Either both ends go up forever, either both ends go down forever, or one goes up and one goes down. And we want to figure out which is going to happen, because this is going to help us get the graph of it tomorrow. So what you need to do in your notes is sketch these 4 pictures. And the middle little dash is not important right now. It's the ends that we're worried about. Okay, so you can put a big squiggle in the middle. It doesn't matter. The ends are the 4 things that can happen. Either both ends go up, both ends go down, left goes down, right goes up, left goes up, right goes down. Those are going to occur based on your leading term. That's why it's going to be called the leading term test. Our degree is n, and it will be either even or odd. And then a sub n will be our leading coefficient that we just talked about. And it will either be positive or negative. So you can see that next to each of these pictures. Either the degree is even or odd. Even ones both go in the same direction, both up or both down. Odd ones go in opposite directions. And then the leading coefficient is either positive, so like this first one, greater than 0 is positive, or it's negative. If I have an even degree and the leading coefficient is positive, just from that leading term alone in the polynomial, I can say both ends are going to go up. If it's even and there's a leading coefficient that's negative, both ends are going to go down. If it's odd and positive, it's going to go up from left to right, like our basic cubic function. If it's odd and negative, it's going to go down from left to right, the opposite of our cubic function. You want all 4 of these pictures in your notes, I promise you. All right, so I'll give you a minute to get those written down. Here we got the 4 pictures. Okay. So we're going to add one more thing to our pictures. We're going to add the formal way that we're going to state both ends go up or both ends go down or this side goes up or this side goes down. There's a formal mathematical way to write that. It's called end behavior. Here's how it's always going to look to start. X approaches negative infinity and X approaches positive infinity. So when you get to calculus, they're actually going to put above this a little LIM. If you have friends in calculus, or if you did like the regular pre-calc last year, called a limit. So when we say the limit as x approaches negative infinity, our book doesn't use LIM. It just uses the x's. But when we say limit as x approaches negative infinity, that means my x is going to the left forever. Okay, or if I say x approaches positive infinity, that means my x is going to the right forever. So this is a left-right situation, and it's always going to look like this to start. Your job is to say, as it goes to the left, or as it goes to the right, what's happening with the y? Is it going up forever or down forever? That's an end behavior. Okay, now in this first picture, both ends are going up. So both of my y's on the left and on the right are approaching, and this is the part you would fill in on like a test or a quiz, the positive infinity. They're both going up forever. If I look at the one next to it, it's going to look really similar. Limit x approaches negative infinity, limit x approaches positive infinity, and again, we don't really need to write the limit. I'm just putting there because that's what the calc book will eventually do for you. And again, we're going to say, as we go to the left and as we go to the right, what's happening to the y's? Well, in that picture, they're both going down. So my y's are both approaching what? Negative infinity. Okay. The two cases where they're odd. On the left, what's my y approaching? As x approaches negative infinity, as we go further to the left, what's my y getting close to? Negative infinity. And on the right, what's my y doing? Positive infinity. It's going up. The last one's just the opposite. As x approaches negative infinity, y approaches positive. On the left, it's going up. And on the right, it's going down. That's what you need to write when you're asked for end behavior. So what you need to be able to do is look at a polynomial and find its leading term. You need to know, is the degree even or odd? Is the leading coefficient positive or negative? And you're going to think about one of these 4 shapes. When Mrs. Solarchek does it, she makes her students do like hand motions. Both up, both down. You know one of those 4 shapes, okay? If you know those 4 shapes, you know what's going up and down and what's going up and what's going down, and you should be able to then picture it enough to write end behavior. So let's try it, okay? It's called the leading term test. The only information we need from this polynomial is the leading term. My first one is negative x to the 4th. That is my leading term. Do you want to do the hand motions? Yeah. What do you think it's going to do? It's a negative in front, and it's the degree. What's the degree? Even or odd. That's what's important. Okay, I have an even degree and a negative leading coefficient. Okay, that's all you need to know. Okay, so my leading coefficient is negative. My degree is even, and it's going to look like this. Good? Like an upside down parabola. Once we know that, let's list our end behavior. I'm not going to use the limit. I'm just going to write it like this. X approaches negative infinity, x approaches positive infinity. Remember, that means on the left and on the right. What's the y doing on the left? What's the y getting close to on the left side? Negative infinity. What's the y getting close to on the right side? Also negative infinity. All right, see if you guys can do the next one with your partner. Well, there's stuff in the middle we don't know. Just right now we're focusing on the ends. Tomorrow we're going to add the middle, and then we'll have a whole polynomial. Okay? All right. Try the next one. Find the leading term. Determine if the leading coefficient is positive, negative, degrees even or odd. Find your end behaviors.
It's odd and negative. Look at your thing. You know.
Oh, the actual numbers. No, I said it's just negative.
Did we get it? Yeah? All right, what shape's it going to make?
Yeah, they come down and then up together.
It's going to go from left to right down. It's a cubic function. You can see it's a cubic function, but it's flipped there. Yeah. Okay, so answer? This would be sufficient work for a problem like this. Stating what you know about the leading coefficient, stating what you know about the degree, sketching the ends. Again, the ends are the only thing that's important, really. And then I'm going to look for 4 things in each end behavior. What x is approaching and what y is approaching on each side of your graph. So there's going to be 4 arrows when you do this. Any questions on that? Okay. Last thing I have for you today. Absolute last thing, and we'll finish this lesson up tomorrow. So I mentioned we've got the ends now. We're going to put pieces of information together about what's happening in the middle. In the middle, we got a bunch of x-intercepts. If we can find the x-intercepts, we can get enough to sketch the graph. Finding x-intercepts is review. How do you find an x-intercept? 0 in for y. All right, let's do that. Plug 0 in for y. And we've solved a bunch of these, but it was always a quadratic. Now they're going to be bigger. It's going to be a polynomial. So it's not, it might be a 2, but it might be a 3 or 4 or 5. You need to be able to factor something like this. In any factoring problem, the first thing you should look for is, do they all have something in common? Do these all have something in common? X in 2. Let's factor it out. If I factor a 2x out, what am I left with? Yes. And can we factor that more? Great question, Grace. What is it? It's factored. Can you tell me what the x-intercepts or the zeros or the solutions or the roots? We're going to have all these different words for it. They all mean the same thing. X equals 0. Don't forget that guy. 3 and 5. If I set each of those equal to 0. Okay? And you can always plug them back in, make sure you get 0. If you have graph and calculator, you can check that's where it's touching the x-axis. All right, let's look at the next one. Plug 0 in for y to find the zeros or the solutions or the x-intercepts, whatever we call them. Do all 4 of these terms have something in common? Ooh. But there are 4 terms. Do you remember how you factored stuff when there were 4 terms? There was a special case, starts with a G. Grouping. What do the first 2 have in common? X squared. And what does that leave me with? Okay, what does the next pair have in common? 2. And what does that leave me with? If you are factoring right, you should get that same parentheses twice. Here are your factors. The first one is 2x minus 3. The other factor is the stuff you factored out. X squared plus 2. What the two things I factored out, x squared plus 2, were the things I took out. 2x minus 3 was my other parentheses. Set them each equal to 0 and you have your answers. If I set 2x minus 3 equal to 0, what do I get?
Where did the things in the front go? Did they just disappear?
They are right there.
Oh.
If you FOIL that back out, you will see you get all 4 of the original terms from your polynomial. You can always check that you did it right by FOILing.
Where the other thingy?
Nope. Nope. It's saying x squared is multiplied by 2x minus 3, and 2 is also multiplied by 2x minus 3. So we can write it in a condensed way. We can say both of them are multiplied by 2x minus 3. That's what that means. That's why there's print. There we go. Look at all the light bulbs going off. What are my answers? What is x equal for this one? Yep, 3 halves, 1.5, yep. Be careful on this one. X squared equals -2. So x equals plus or minus the square root of -2. Now, if we're looking for real solutions, we don't get any from there. There are imaginary solutions. When we have a negative under a square root, we'll talk about that in the later section. So for right now, if we just want real zeros, real solutions, 3 halves, 1.5 is going to be the only one that you're going to see on the x-axis.
Do you want us to solve?
No, this one just said real zeros. So as soon as you realize it's not real, you can just stop and say that's the only one that's real. All right, I'm going to give you 2 of these problems as a warm-up tomorrow. That's where we're going to start off, and we're going to put the last couple pieces of the puzzle together to be able to graph one of these big polynomials without a calculator. That's our goal for this lesson. Okay, that's where we're leading up to. And you'll get a little handout tomorrow, don't worry, so you'll have a graph paper and everything. All right, we got 10 minutes left. Do you want to see your tests? No? They were pretty good. You want to know what your average was?
Pretty good.
I mean,